What do we do? Well, turns out, shocking, that ENOT cell tells us a lot. It really does. So I calculated an ENOT cell. What the hell is that? So back on slide 4, I said that electrons flow spontaneous. Potential. What is spontaneous? Well, spontaneous per 17.2, which we're going to cover for the next exam, is a reaction that does occur under a given set of conditions on its own. We don't have to do anything. We'll talk about what those conditions are later. So how do we know if a redox reaction is spontaneous? Well, E cell will tell you what that is. Now, E cell is similar to E not cell, okay, but it's not under standard conditions. So what do we mean by standard conditions? Well, this E not cell that we're talking about, which is what we've been calculating, is standard production potentials. And again, that's 1 molar concentration or 1 atmosphere for gases. So there is a concentration component that goes with them. All right? Now, each cell is not the same. So it's related to the values that we would calculate under standard conditions, but we don't necessarily have the correct values. So it's not 1 molar or 1 atmosphere. Okay? It's going to be slightly different. And E cell can be anything, just like we've seen before. We're really dealing with a Q situation rather than a K situation. Now, if E cell is greater than 0, then it's a spontaneous reaction. It's a galvanic cell that goes in the forward direction. If E cell is less than 0, it's a non-spontaneous reaction. That's called an electrolytic cell. And just as a point of note, voltaic cells could be either one. Galvanic is spontaneous. Electrolytic requires electricity to be put into it, so it's a non-spontaneous. If it's non-spontaneous, it doesn't happen on its own. We've got to pull electricity into it to get it to work, such as recharging a battery. So that's the negative direction on that. And we have to supply the energy to get it to charging. Cool. Awesome. All right. Questions on that? Okay. So mud. How is that? What are we going to be looking at when we talk about non-standard conditions? Well, so far, we've talked only about standard conditions. 1 molar for solution, 1 atmosphere for gases. What if I'm not under those conditions? For reasons we'll talk about in chapter 17, we can calculate what will happen if we're under non-standard conditions. So it could be any part of the reaction. We could change one concentration or both. Any of them. We need to have a way to look at that. And that was Q. Remember, Q was for any non-equilibrium conditions. And so there's going to be a driving force to get back to equilibrium. And that's going to affect the E that we're looking at. So this E, the non-standard, is going to be related to the standard minus 0.0592 over N times the log of Q. Okay. I can calculate a cell for non-standard conditions to see if a non-standard cell is spontaneous or not. I can do that. Absolutely, I can do that. And I can also look to see what effect changing that concentration had on the driving force of this reaction. And I think that's pretty cool. Of course, most of my PhD thesis was about the Nernst equation, so there you go. And that is called the Nernst equation. Just so Nernst equation is E equals E naught minus RT over NF ln of Q. Since we can talk about standard conditions, we have fixed temperature, which is 25 degrees, not 0, 25. This one's 25. That gives us that 0.0592 over N. That's incorporating R, 25 degrees, and F, which is the Faraday constant, which is on table stuff, times the log of Q. So let's consider the following cell diagram. So we have MgS and MgSO4, 0.4 molar, and NiSO4, 0.6 molar, going to Ni. Now remember, those two concentrations, that tells us exactly what's in our beakers. So they're non-standard. Awesome. I said they would be molar. So we can calculate the cell voltage at 25 degrees. So E cell equals E naught cell minus 0.0592 over N log Q. When I look at this, I see that it's a 2-electron process because we go from Mg to Mg2 plus and from Ni2 plus to Ni. So that's a 2-electron process. My Q is going to be products over reactants. And so my product is the NiSO4. My product is the MgSO4. My reactant is the NiSO4. Remember, when we talk about the cell notations, this is my reactant here, this is a reactant here, this product here, and that's a product there. So it's going to be the MgSO4 over the NiSO4. And so we get the 0.4 over the 0.6, which is exactly what I said it was going to be. So the product is the Mg2 plus, the reactant is the Ni2 plus. The E naught cell equals 2.210 volts. Okay, for our standard. So Mg2 plus and Ni2 plus to Ni. That's 2.12 volts. And I'm not going to show that calculation. And so our E cell equals 2.12 volts. Okay, so we go up a little bit because of this. Now, what does that mean? Well, we go up because we don't necessarily have a product. So we are pushing to get to that product. So that's why we go up. Okay. Now, how does the voltage change when Mg2 plus is decreased by a factor of 4? So my Mg2 plus goes from 0.4 to 0.1. My E cell, if I do all of that math again, is 2.143 volts. How does the voltage change when Ni2 plus is decreased by a factor of 3? So my Ni2 plus goes from 0.6 to 0.2, and that gives me a 2.11 volt. And if Ni2 changes after the Mg2 plus, so Mg2 plus is at 0.40 over 4, which is the 0.1, which we calculated in the first part. The Ni2 plus equals 0.60 divided by 3 equals 0.20. And so we're then going to have a situation where we're looking at 0.10 over 0.20, and that will then give us 2.129. So decreasing the product makes the reaction more favorable. So a higher E cell. Decreasing the reaction makes it less favorable. We don't have as much driving force. Okay. Calculate the cell voltage at 25 degrees of a concentration cell consisting of an Ag electrode and 0.5 molar AgNO3 and an Ag electrode and a 1.0 molar AgNO3. What the flippin' hell are we talking about here? Well, a concentration cell is exactly what it sounds like. We have the same system at 2 different concentrations. So my Ag in one case is 0.15, and in the other case it's 1. Okay. So what that means is that I have an Ag that goes to Ag plus, and I have an Ag plus that goes to Ag, and of course products of reactants is going to give me my E naught cell is going to be 0. And the E naught cell is going to be 0 because these two reactions, when I reverse them, they're going to give me an E naught cell equals 0. And so the only thing that I have here is looking at that log Q. Q in this case. Let me make sure. Okay, sorry, just had to check my math. So our product is the 1 mole, and our reactant is the 0.15 molar. And so if I do that happy math, and remember that there's E cell equals E naught cell minus 0.0592 over N times a log of that Q that I have right there. This is one electron process because we're talking about transfer of electron. So that gives me that 0.048 volts. Okay. And so that's our concentrations I'm looking at. So products over reactants. And I say products because this is the second one that was listed, and this is my reactant. So that's how we get that value. Okay? So that's a concentration cell. So we can have a situation where we're looking at the exact same chemistry on both sides. We just change the concentration on one of them. Sometimes that's all we can do in terms of trying to generate electricity. It's not the most efficient thing, but it's a way. So some practice for our concentrations. The value of E naught cell for the following reactor is 1.10. What is the value of the E cell? And the concentration of Cu2 plus is 1 molar, and the concentration of Zn2 plus is 0.025 molar. Zn solid plus Cu2 plus goes to Cu plus Zn2 plus. So we've done that before. We calculated the standard potential. That was 1.10. So it's one of the first ones that we talked about. So my E cell is going to be equal to that E naught zero, that 1.10 volts, minus 0.0592 over 5 over N, which is 2, times the log of Q. My 2 plus, Zn2 plus, is 0.025. I'm sorry. And my product is the 1 molar Cu2. So that gives me 1.10 minus 0.052 over 2 times minus 1.60, which then gives me 1.14 volts. So that is my practices. Go awesome. Second, the value of E naught for the following reaction is 0.189. What's the value of E cell given concentration shown? So I 4H plus Fe solid plus 3NO3 goes to Fe3 plus NO plus 2H2O. So H2O doesn't appear, so I love that. Yeah, Fe solid doesn't appear, so I love that. When we calculate our Q, it's going to be our products, which is the Fe3 plus times the NO minus divided by the H plus to the fourth times the NO3 minus cubed. And if I look at that, that's a 3 electron process that we're doing. So Fe solid to Fe3 plus, so that's a 3 electron process. I have my E naught cell equals 0.189 minus the 0.0592 divided by 3 times the log of this lovely expression right here, which is the log of 23.85, and so that gives me 0.029. So again, it changes. All we need to do is remember to write the Q and remember all of the things that go with that. So we haven't walked away from equilibrium. We're just not using it in the same way that we were. But we still have to remember all of those principles. So we have to remember that the solid stuff, there's product over reactant to their stoichiometric coefficients. And that's the value that we will calculate. So questions, comments, problems on that? Hopefully. Let's try another. Okay. So I'm going to get Mg solid going to MgSO4 0.95 and NiSO4 0.59 to Ni solid. So my product here over reactant. I'm just going to move this because I need to. is going to be my product Mg2 plus over my reactant, which is the Ni2 plus, and that's going to be equal to the 0.95 over the 0.59. Okay, well that's awesome. Let's take a look at the rest of this. So we need to have an Mg solid going to Mg2 plus 2E minus. And if I use my happy cheat sheets, I standard reduction potentials. Mg. If I scroll down, Mg2 plus 2 electrons go to Mg solid. So reverse of this reaction is 2.37. So since this is an oxidation, I choose a sign of the value that I found in the standard reduction potentials table. I also have an Ni2 plus 2E minus going to Ni, and that value is negative 0.26. So my standard reduction potential is that 2.37 minus 0.26, which is 2.11. So my E naught, it's not an E naught, it's an E cell, is equal to E naught cell minus 0.0592 N times a log Q. So that's equal to that 2.11 minus 0.0592 over 2 times a log 0.95 over 0.59. So 2.11 minus 0.052 divided by 2 times the log of 0.95 divided by 0.59. And it gives me 2.10. So not much change, but that's how I would deal with it. Okay. So remembering that we need to deal with one of our products, which is the Ni. Sorry, my product Mg, because it's the second one, and with our reactant Ni, because that's the first one, and then it's a 2-electron process. Okay. Questions on that? Questions, comments, problems. All right. So the next part we're going to talk about when we get to it is thermodynamics. Now I'm going to stop here, and I'm going to set up for the next one. I'll talk to you soon.